Okay, welcome to the walkthrough on refraction, the optical properties of light. It is all electromagnetic waves, but we're just going to really talk about light. It makes it easy to think about. So, Section 3, refraction. Okay, so the whole idea of this is it's to do, as you know from GCSE, about how much light slows down. So, our idea is that we have this measure of a material. Okay, so this is optical properties of a material, and we're going to call it nu is the standard symbol for refractive index. And it's kind of like the optical resistance for a material. So electrical resistance, as I said there, similar kind of idea. How much it is slowing down and trying to prevent that flow of energy. So effectively we do it as a ratio. It's the only way to think about it. So to start with, data book value is that we're going to look at the speed of light if in a vacuum, and then we'll compare it to the velocity in the material itself. Okay, so material in vacuo. Okay, so how much slower does it get in here? This number will always be greater than 1 because you can't get faster than the speed of light. So this is always going to be the largest number, smallest number. Now, examples at the bottom. However, what we can do is, if we relate it to your GCSE, we can measure it in terms of how things move. So we're going to take a basic principle first. And the basic principle is we're going to say air is very, very similar to vacuum when we're talking about speed of light. It's actually about 1.0002, I think. So, to 3 significant figures, it's the same speed in air as it is in vacuum. So when things are travelling along, all good. They travel in a straight line. There is nothing to prevent that. What it's really doing is we have a ray, but it's due to the waves travelling along. Now, an analogy you might have done at GCSE is think of it like a vehicle. It's quite a famous little limerick about vehicles giving a twitch as they bounced off the ditch. So yeah, if we're travelling along a nice straight road, then our car travels in a nice straight line. So looking down, here's our 4 wheels. However, when we hit something where the speed slows down, then if you are travelling, so you hit one wheel first, that side will slow down first. Okay, and here's where our spin comes round. If you then come through the mud and come off the other side, or if you're already in the mud and you're coming out of it, you get a grip on the side that hits first, and that speeds up first, so we have a change in direction away. So at GCSE, refraction was just about this bending ray, but we actually compare it to the normal ray. So if a ray hits normal to the surface, if it is a normal ray, then what we get is a ray that travels in a straight line, hits the surface dead square, and yes, it does still slow down, it does still speed up, but it doesn't change direction. And because of that unique property, we measure all angles from that normal line. Okay, so nothing special, but it does mean it's quite easy that when we have a curved surface, we can still work out where the normal is, because light will just travel straight through at that point. Okay, when you watch the video of the experiment for this, then you'll see that on the curved surface it will just go straight through and carry straight on as long as it's hitting at 90 degrees. Just point out at GCSE, according to GCSE, that was not refraction, but it is. It's still changing speed, so it's all, in terms of definition, it is refraction. So what we're going to do here is we're going to look at the idea and try and come up with a far better, more useful way of thinking about it. And the way to do it is actually to compare materials. Okay, and this just gives a much more powerful generic way of dealing with things. So we have a speed 1, we have a speed 2. From our idea, if you can visualize it, we've slowed down, so we've slewed a bit straighter. Might be an idea of thinking about like ice skating if you're coming up to a barrier. as you grab it with one hand, you spin round and change direction, you face into the barrier more. So here's our boundary across the surface, we come in, we hit the boundary and we change its direction. Now, you can use the maths to work it out if you can't visualise easily too much about it. But we've got one angle, we've got a second angle because we've got a different speed. We need to work out how this bending of light gives us this change in speed. So what we're going to do is we are going to take this diagram, but we're going to look at it in waveform. So we're going to zoom right in. So instead of a little ray like this, we're actually going to zoom in so we end up with a big fat ray. So what we need, and I'm going to make it very obvious because we need to kind of think about this, we need to have a ray nice and parallel sided, okay, big fat ray coming in, and then it's going to change and hit with that same angle. Okay, so again parallel inside. So when we're inside this second material, we've got a parallel ray. When we're outside, we've got a parallel ray. Okay, so very carefully use a ruler for your diagram, makes all the difference. Now you might notice that actually the ray does get fatter, and if you can remember back to when you did this at GCSE, you would have found the ray inside the block of material was slightly more blurred, slightly wider, slightly less defined. So this actually does mimic what goes on in real life. So what we have here is, I'm now going to totally cheat, and I'll show you why. So just to make clear, there's our first refractive index, here's our second refractive index. So what we are going to do is look at the idea of relative. So basically what we do is a symbol often used like this, more in some examples than ours, but we're going from material 1 into material 2. It could be in a vacuum or air going into glass, for example. Now, what we've got going on is our ray is actually made of waves. Now, this is where the cheat comes in. I am going to say that that is the wavefront. So just like standing on a beach, you can see the tops of the waves. Here is a peak of a wave travelling inwards in this direction. Okay. Now, the cheat is, if I happen to make the wavelength that long, so in other words, exactly the same as that length to there, then I can make my maths so much easier. So there's the point. So here's one wave, here's the one behind it, again nice and perpendicular, okay, so it's 90 degrees, so there's your waves washing forwards, okay, and if you want to, you could do it the same distance again, and again, just use your pen, gives that same kind of mark, okay. So we've got a whole series of ripples coming in, a whole series of waves, and what you'll see is they are of a certain distance apart, which is of course the wavelength. Okay, now this will change, so this is the wavelength in the first material. The wave that's in front of this one has completely gone into this next material. So using our analogy of the car, yeah, we're not at the point where one wave is on the mud and one corner is on the mud and the other wheel hasn't quite reached there. We're actually considering either totally off the mud or totally in the mud. So our wave here is completely out of this second material, but the wave in front has, or this side of it, has literally just reached there. Okay. Now, because we assume that the wave fronts are exactly 90 degrees, then what we can do is we can draw that wave front there. Okay. Now, the distance it's travelled in a certain time is the wavelength. In one time period is the wavelength. This one hasn't travelled as far, so it's a shorter wavelength. But all the way through, as long as it keeps travelling at the same speed, that wavelength will be the same. So just like if you come off a motorway, cars get closer together, maybe not at Barnsley because they always stop on the roundabout, but normal place, if you get off the motorway and you slow down, cars tend to get closer together. So using that same idea of marking, what we're going to do is just draw out the fact that we have a series of waves that are now inside the material travelling forward in that direction. Okay, and they have a new, much smaller wavelength. Okay, so I'm going to call it the second wavelength. Now, key point, the wavelength changes because it's slowing down. The colour is still the same. So if this was a red ray, this would be a red ray. If you're in water and you see someone bobbing around in a swimming pool down the Metrodome, and you'll see someone in red swimming trunks as they're walking around the pool, they're in red swimming costume. If you happen to be swimming under the water and you see them again, you'll still see it's red. The colour has not changed. So what we've got, for those that are a bit sneakier, will have realised I have cunningly made this so if I was to draw on a normal, this is supposed to mimic that. So that's obviously the same angle, the incident angle, the first angle. We're not going to worry about incidents generally. We're just going to think of first and second. And the one inside, well, that's my θ2. Just put it in a neat place. And cunningly, I have two right angle triangles. Brilliant. So what I've got is here is θ2 as well. Okay, so the small angle, it's opposite to it, and so that means a bit harder to spot from the one I've done, but this is θ1. And what they've got, they share the same wavefront, they share the same distance, the meeting point on the glass, because it's the same ray. So I'm going to just call this length, doesn't matter too much. Okay, so that is from here to here. But what I can do is I can start to think about how far it's travelled, the wavelength, in a certain amount of time. Just happens to be the time constant, but that doesn't matter. So let's make this up and let's think about the bits that matter, where it is changing. Okay, so θ1 I can put in terms of the sides of the triangle. So if I take the opposite to the angle, that's going to be sine of θ1. Okay, so sine θ1 equals the opposite, which is the wavelength, wavelength 1, over the hypotenuse, which is our length L. Down here, same thing, wavelength is the opposite, so sine θ2 equals wavelength 2 over that intermediate length. Okay, so we can start to do some maths that's useful from it, having constructed our diagram. Okay, so our wave diagram. So the derivation, let's go with this. Nice and straightforward if you think about it. So I should say, for the wave shown, you can do it where the a wavefront, for example, splits across the surface. You end up with smaller triangles, just a bit more awkward, etc., etc. But it can be done. But for this wavelength that we've shown, sorry, for this wave that we've shown, our refractive index is defined at going from material 1 to material 2 is actually a conversion of the two. It's looking at the change from 1 to 2. So what you do is you find the ratio. Oops, excuse me, that's terrible. Yep. So my refractive index of the second material divided by my refractive index of the first material. They should be the same symbol. That is very mucky, excuse me. So, from our definition on the previous page, the refractive index for 2 is speed of light in air divided by the velocity in material 2, divided by speed of light in air velocity 1, which is of course the same as multiplying velocity 1 over c2 over c, sorry. Okay, so those cancel. Just consider that before I cancel it. So yeah, I've just flipped that upside down because dividing by a number is the same as multiplying by the reciprocal of that number. So that's velocity 1 over velocity 2. Great. What does that mean? Well, it tells us how far we've travelled, this displacement. Okay. Normally we use the letter S for displacement, but we haven't done motion so far, so I'm going to skip it around. So I'm just going to put, for a bit more information, for one cycle, so for one complete rotation of that wheel idea, the distance travelled is equal to the wavelength. Okay, so I'm just going to put that in bracket there to help us, because then I can get velocity 1, distance 1 over distance 2. So that's going to be wavelength 1 over time divided by wavelength 2 over time. Now I know I normally say avoid this, but might as well make it nice and easy. They're both the same, so again we can ignore that. So let's sum it up. That's a useful kind of play, but where we actually want the detail, just going to put in the corner here, for our definition of a refractive index changing from material 1 to material 2, it is, from here, the comparison of the wavelengths. Okay. Which happens to be, if we take from these, a rearrangement, length times by the sine theta 1 over length sine theta 2, because it's wavelength 2. Okay, so take the L across. And so what we can find is that ratio of there is actually just the ratio of the sines. Okay, and that is a really powerful, well, that's a fairly powerful law. Even more powerful is if we compare it to what we've just had up here. This is far more useful. So you can have refractive index 2 divided by refractive index 1. Okay, now that is a beautiful, really powerful equation, just ignoring this idea ratio, because it tells us as long as we know one of the refractive indexes, we can work the other one out. Okay, so the second part of our refraction practical is where you are using one answer for the perspex block in my video to then find the second one, which is basically telling us about the speed of light in different materials, okay, different liquids in this case. So if you're thinking, oh, that looks just a bit hard work, well, it should become a bit clear, because if we think about that, we can simplify it a little bit. So what we can do, he says, I've just managed to lose my next page, there we go, is that we can simplify it into a much more powerful equation. So if we take those and cross multiply, okay, just move that in a little bit. If we cross multiply, then what we're saying is refractive index 1 sine theta 1 equals refractive index 2 sine theta 2. And that is a really useful equation that can deal with all kinds of difficult questions like this, and total internal reflection that we're going to get into. But even more beautifully is that if we had something like this scenario, like in my picture at the start, if we have water, for example, inside a glass container with air on the outside, well, this whole idea works really well together. And if, for example, this one we had, and I'll just put e.g., refractive index of water, which is about 1.33, depending on temperature, I should say, is the sine of the angle in water. Well, that goes into glass, so that's the refractive index of glass, sine theta in the glass, equals refractive index changing over to the next one, where we've got air, sine theta air. And so effectively I can cover that up. So the water and the air give us those angles. So effectively what I'm saying there is actually if we have parallel sided container, then we can ignore the container because the angle there and the angle there will still be right if there was no container. So if the water could magically finish on the edge of air, okay, be surrounded by air and just stay there, just like when floating around the International Space Station, for example, then what you'll find is that the angles will still be exactly the same. Okay, and there's a few instruments that you do that to try to find out refractive indexes of things sandwiched between layers of glass, etc., etc. But really, really powerful because we can just consider one surface, one side of a surface, and then maybe 4 or 5 layers later, another surface, and you can still compare something over here to something over here, whatever that substance is. Okay, so really, really powerful, simple equation. The proof itself was actually came about almost 2,000 years ago with the ideas of this. It wasn't done with trigonometry because that wasn't invented till later, but ratios of triangles and the idea of the from Mesopotamia about waves being an idea of light. We can use that to find out how much things bend. Now we can link it to how fast things travel, because if you know your refractive index, then we can go back to that and we can work out the speed of light. Okay, so short, very, very powerful and very useful idea. At this point, what you really need to do is have a practice with these questions. So have a look at the section on refraction, okay, and in the workbook. And here's some simple ideas here, so get used to that basic equation, then get used to the boundary equations, okay, a little bit rounding up. Then this one's going from water into glass, okay, and then, even more challenging, you can start to think about where it gets more geometrical. But again, it's just doing the first step, the first refraction, then we've got a second refraction, and things like that. Okay, so it's quite a nice logical section. It's just breaking it down into steps, and I cannot overemphasize how useful that, or shall we say, the cleaned up version is. Okay, learn that. It is an awesome equation, a really, really useful equation for properties, optical properties of materials.